Good afternoon, everyone. Once again, welcome to the fourth and final session of heat and mass transfer. In previous sessions, we have covered four chapters, including conduction, lumped heat analysis, heat transfer through fins, convection. And today's final chapter, we will be trying to cover these two chapters, the remaining chapters of radiation and of heat exchangers. So let us start conduction, convection, and radiation. Conduction takes place predominantly in solids. However, it also takes place in gases and liquids as well, but it is mainly seen in solids. Convection is widely seen in fluids, be it liquid or gases. So convection is the predominant heat transfer phenomena in the medium of liquid and gases. Now comes radiation. What is radiation? Radiation is the transfer of heat by means of electromagnetic waves. Electromagnetic waves are not mechanical waves like sound waves. Sound waves need a medium to propagate. Sound wave have a different speed in different medium. However, electromagnetic waves do not require any medium to propagate. Hence, the radiation heat transfer is the only heat transfer that can take place through vacuum as well, and this is the mode of heat transfer responsible for propagation of heat from sun to earth. And I told you that each and every mode of heat transfer has its own governing law. हमने देखा था कि हर एक हीट ट्रांसफर के लिए एक स्पेशल हमारे पास गवर्निंग लॉ है. फॉर कंडक्शन it was Fourier's law. For convection we had Newton's law, and for radiation there is a law called as Stephen-Boltzmann's law. So let us just start the study of radiation by its governing law. So the Stephen-Boltzmann law states that the radiation energy emitted from the surface of a black body per unit time per unit area. So heat the energy is what we have in heat transfer. We are concerned mostly with heat energy. So heat energy per unit time, per unit time per unit area. So joule per terminology is known as emissive power. So this terminology is known as emissive power. Now, why do in the very first place we need emissive power? Because let's suppose we are talking about sun. Sun is a very huge entity. So this entity has a big surface area. So instead of, and we won't be receiving the energy from all of its surface area. So the earth may receive from particular surface area. So what we need is how much an average value that the sun is emitting from over a distributed surface. Fine. So yes. So the Stephen Boltzmann says that this emissive power of a black body. I will tell you what a black body is, and we have also studied it in our school about radiation and black body. But let us just get back to Stephen's Boltzmann law. So this law states that the emissive power of a black body is directly proportional to the fourth power of the temperature, or to be precise, it is absolute temperature. It is absolute temperature. Now, what is absolute temperature? Absolute temperature is temperature measured in Kelvin. So this value here is in Kelvin. So EB is directly proportional to T to the power 4, where T is measured in Kelvin. EB, again, now if we have to remove this sign of proportionality, we need to introduce a constant of proportionality, and the constant of proportionality here is sigma. This sigma is known as Stefan-Boltzmann's constant. Stefan-Boltzmann's constant. Its value is 5.67 into 10 raised to power minus 8, and by rearranging we can find that its unit is E upon T to the power 4. So what is unit of E? Unit of E is watt per meter square upon Kelvin to the power 4. So it becomes watt per meter square Kelvin to the power 4. So Stefan Boltzmann constant has a value of 5.67 into 10 raised to power minus 8 watt per meter square Kelvin to the power 4. Now, what is a black body? We came across a terminology named as black body. So suppose I have a body here, and this is the amount of some amount of heat energy that has been incident upon this body. If this body absorbs all this heat energy, then this body is known as a black body, or a perfectly black body. A black body is a body which absorbs all the thermal radiation incident on, or the falling upon incident or falling upon the body. Okay. Now we have to look some terminologies, including absorptivity, transmissivity, and reflectivity. Suppose I have a body here. Now few amount of heat is incident on this body. Q is the total amount of incident energy. Incident radiation, heat radiation, or thermal radiation. Terminology is quite mixed up, so don't get whatever we are talking about. Radiation is thermal radiation. Thermal radiation is nothing but uh, or, thermal radiation is nothing but the heat energy that has been radiated. QA is the amount of heat absorbed. QR is amount of heat reflected. We need to change pen. Okay. QR is heat reflected, and QT is the amount of heat transmitted. Now what happens to this body? Some amount of heat energy is absorbed within the body. That is QA. Some amount of energy is actually this body allows to transmit through itself. That is QT. And the remaining amount is reflected. So when Q total amount Q of incident heat radiation falls upon this body, some of it is absorbed, some of which is reflected, and some of it is transmitted. So let us now keep this in mind and jump to this terminology. The very first terminology here is of coefficient of absorption. Coefficient of absorption. What does it say? It is the ratio of amount of energy absorbed to the total incident energy. So let's say if the incident energy was 100, and this body absorbed almost 600 watts, and this absorbed 60 watts. of energy. So alpha will be 60 upon 100 and its value will be 0.6. Now coefficient of transmission. So coefficient of transmission is the ratio of amount of heat transmitted to the total incident heat. Now again the incident heat was 100 watt, then the absorbed heat was 60 watt, and the transmitted heat was, let's say, 10 watts. So it will be 10 upon 100, which will be equals to 0.1. The value of tau here will be 0.1. Now again we have QR. QR is the amount of heat that is reflected. QR is amount of heat that is reflected. So out of 100 watts, 60 watt was uh, absorbed, 10 watt was transmitted. So remaining 30 watts are what? Reflected. So amount of energy reflected divided by total incident energy, that is 0.3. So this is coefficient of reflection. It is very easy to remember this. If you just remember these equations, you can easily remember its definition. How? Alpha is the ratio of absorbed heat energy absorbed by the body to the total heat energy incident on the body. Transmissivity or coefficient of transmission is the ratio of amount of heat transmitted to the total amount of heat that is being incident on the body. Reflectivity is the amount of heat reflected to the total amount of heat incident on the body. So let us just move further and continue this discussion about these coefficients. So as I told you, Q is the amount of heat that has been incident on this body. QR is reflected. QT is transmitted. QT is the amount of heat transmitted, and QA is absorbed within this body. QA. Okay. So total energy is equals to energy absorbed by the body plus energy reflected by the body plus energy transmitted by the body. Okay. Now what I will do, I will divide the above equation by Q itself. So by rearranging, I can write QA upon Q plus QR upon Q plus QT upon Q is equals to Q upon Q. What is QA upon Q? QA upon Q is, if you decipher this equation, it is heat absorbed upon total heat, that is absorptivity. Heat reflected upon total heat, that is reflectivity. Heat transmitted upon total heat, that is transmissivity. Absorptivity, reflectivity, and transmissivity. And what is Q upon Q? It is 1. So this is a very important equation that we have achieved. The summation of all these coefficients, that is coefficient of absorption, reflectivity, and tau, is equals to 1. Let us now check this equation with various cases. What is our equation? Alpha plus rho plus tau is equals to 1. First of all, let us see black body. Now, what black body will do is, if Q is the amount of energy incident on it, then it will absorb all the energy within it. So we can say QA is equals to Q. So alpha, which is QA upon Q, becomes 1. If alpha is equals to 1, then in this equation, alpha plus rho plus tau, we can say that rho is equals to 0 and tau is equals to 0, because their combined summation should be equals to 1. Since alpha is taking the value 1, the remaining two will have a value 0, as they can never have negative value. So these values will be 0 and 0. Now again, now let us see what is with this black body, sorry, white body. Now when Q amount of heat is incident upon it, what this white body will do, it will reflect the same total an amount of energy that is equal to the incident energy. That is, we can say QR equals to Q. Now rho is what? QR upon Q, which is equals to 1. Now since rho is taking this value, so again from this equation we can say that alpha is equals to 0 and tau is equals to 0. Now let us move towards the next term, that is transparent body. Now in a transparent body which is not absorbing any kind of heat, we can say that if Q amount of heat is incident upon it, then the same amount of energy will be uh, allowed to transmit through it. So we can say Qt is equals to Q. Then tau will become what? Qt upon Q equals to 1, because this is Q. Here also this was Q. This was also Q. So the value of tau will be 1. So the remaining value of alpha and rho will be equals to 0. Now let us see what is an opaque surface. An opaque surface is a surface which won't transmit any heat, that is Qt equals to 0 in this case. So the energy is either reflected or absorbed by the body. So Qt is equals to 0, that means tau, that is Qt upon Q, is equals to 0. So what this equation becomes, this equation 1, I will say from 1 we can write alpha plus rho equals to 1. So this was discussion about different types of bodies that we come across in this radiation heat transfer. Now Planck's law of thermal radiation. Now, this is kind of a law which is related to the nature of wave. So one must know that, one must remember that this heat transfer is special because it takes place by means of electromagnetic waves. Since we are talking about waves, there will be terminologies like wavelength, amplitude, etc. that will come into play when talking about this type of heat transfer. So what is this law states? Let us just quickly read it. This law states that monochromatic emissive power of a black body is dependent on both absolute temperature of black body and also on the wavelength of radiation energy emitted. तो ये क्या बोल रहा है कि जो आपकी इमिसिव पावर है, मोनोक्रोमेटिक इमिसिव पावर, दैट इज ईबी इज इमिसिव पावर of a black body. What is monochromatic? Monochromatic is actually, it is related to some particular wavelength. किसी एक पर्टिकुलर वेवलेंथ पे अगर आप इमिसिव पावर देख रहे हैं ब्लैक बॉडी की, सो इट इज डिपेंडेंट ऑफ व्हाट? इट इज डिपेंडेंट ऑफ the absolute temperature and the wavelength. So it is the function of temperature and wavelength. So let us draw a graph here. So here we have monochromatic wavelength EB lambda, and here we have wavelength lambda. This is temperature T1. For this temperature T1, maximum value here is EB lambda 1, and lambda m lambda m1 is the value of wavelength which has the maximum value of monochromatic wavelength for this temperature T1. मतलब क्या है, लैम्बडा एम को समझ लो पहले. लैम्बडा एम एक ऐसी वेवलेंथ की वैल्यू है जिसपे आपकी जो इमिसिव पावर है वो मैक्सिमम रहेगी फॉर दिस पर्टिकुलर टेम्परेचर. तो अगर टेम्परेचर यहाँ पर लेट से 2000 केल्विन है, तो इसके लिए ईबी लैम्बडा की वैल्यू, मैक्सिमम ईबी लैम्बडा की वैल्यू अलग रहेगी और लैम्बडा एम की भी वैल्यू अलग रहेगी. देन वी हैव टेम्परेचर T2. फॉर दिस टेम्परेचर this is the maximum value. I think let us switch the pen again. The graphs are not drawn properly. This is not the nature of graph here. Just check the graphs. So yes, this is how it looks. Once the value reaches maximum value, then it keeps on falling down. So this is for temperature T1, T2, T3. Corresponding value is lambda m3, lambda m2, lambda m1. Okay. So by experimentally it was found that lambda m, or the wavelength at which the EB lambda has a maximum value, is inversely proportional to temperature. जैसे जैसे टेम्परेचर की वैल्यू कम होती जैसे जैसे टेम्परेचर की वैल्यू कम होती जाएगी वैसे वैसे लैम्बडा की वैल्यू बढ़ती जाएगी. So we can say that lambda m into T is equals to constant, and this is Planck's law. Fine. What is the importance of if you want to remember it, what you have to remember is just this statement, just this expression, that EB lambda is function of absolute temperature and the wavelength. Now emissivity. Now there is this term known as emissivity. Emissivity is the ratio of the emissive power of a black body to the emissivity of a body is defined as emissive power of a body to the emissive power of a black body. So let us just understand, we have two bodies, one is a black body, one is a normal body. This body has an emissive power of, let's say, 100 watt per meter square. Now the temperature here is, let's say, some 1000 Kelvin. Okay, that is just an assumption, that is not the exact value. And at the same temperature, the normal body is having an emissive power of 70 watt per meter square. So emissivity of this body is what? इसका खुद का इमिसिव पावर, और इस टेम्परेचर पे एक अगर ब्लैक बॉडी होती इसके जगह, तो उसकी इमिसिव पावर जो रहती उसको हम डिवाइड कर देंगे. सो इसकी इमिसिविटी क्या होगी? 0.7. सो व्हाट इज द पर्पस ऑफ इमिसिविटी? Emissivity is nothing but it is a standard of comparison. So in any case we need to evaluate something, then we have to set a benchmark for comparison. So black body is that benchmark which we are going to compare with for any body. So emissive power of any body can be compared with the emissive power of black body for by means of emissivity. Now, fine. Another law in this radiation chapter that we have also studied in school is Kirchhoff's law. Now, Kirchhoff's law of heat radiation states that the emissivity of radiating bodies is equal to their absorptivity. So, for radiating body, their absorptivity is equals to their emissivity. That is, alpha is equals to epsilon. Now, under the light of this law, what will happen to an opaque surface? We know that for opaque surface, a transmittivity is 0, that Q will only be reflected and absorbed. So what we can say, alpha plus rho plus tau equals to 1. This is our equation. Now tau is 0. So alpha plus rho is equals to 1. Now rho is equals to 1 minus alpha. Using the same thing, we can say that now this alpha is equals to epsilon, the emissivity. So rho is 1 minus emissivity. So this is it. So this is Kirchhoff's law, and this is what we can get from Kirchhoff's law. Now moving forward, all those with those first this question gets asked in the exam. It has been asked. What is Jupiter? This is our sun, and this is our Earth. Okay, is the all amount? Can you tell me if all the energy that has been emitted by the sun is all been absorbed by Earth? The answer is no. Not all of the amount of energy is absorbed, but some fraction of that energy is absorbed on the Earth, or that comes to the Earth. यानी कि अगर सन है तो सन की सारी एनर्जी हमारे अर्थ के ऊपर नहीं आएगी. अर्थ ऊपर आए. स्टडी करने के लिए हमारे पास है शेप फैक्टर. तो शेप फैक्टर को हम डेजिग्नेट करेंगे Fij. We will designate it as Fij. Let Fij be the shape factor where I and j are two surfaces, where I is one surface and j is one surface. Let's say the sun is I and the earth is j. So what this Fij means? This Fij means that it is the fraction of radiation leaving from surface I that strikes surface j. मतलब surface I से जिस फ्रैक्शन ऑफ एनर्जी जो निकल कर सरफेस जे पर स्ट्राइक हो रही है उसको हम बोलेंगे Fij. Now since Fij is a fraction, then its value will be greater than 0. greater than or equal to 0 and less than equal to 1. Fine. So this is what we have to understand. Let us just see some cases. Now this is a flat plane surface or flat surface. Now the for this surface, इस सरफेस से निकलने वाली जो भी एनर्जी है वो वापस इस सरफेस पर नहीं आएगी. इसका मतलब अगर इस सरफेस को अगर हम 1 नाम दें तो इसके लिए F11 विल बी इक्वल्स टू 0. मतलब इस सरफेस से निकलकर वापस इस सरफेस पर अगर कोई एनर्जी आ रही है तो ऐसा तो नहीं है कि कोई एनर्जी ऐसे वापस नहीं आ रही. सो दैट इज व्हाई F11 विल बी इक्वल्स टू 0. नाउ वी हैव कॉन्वेक्स सरफेस. अब कॉन्वेक्स सरफेस में भी जब हीट यहाँ से निकल रही है, रेडिएशन यहाँ से निकल रही है, तो वापस वो इस सरफेस के ऊपर नहीं आने वाली. यानी जो यहाँ से निकल रही है वो वापस नहीं आने वाली. जबकि ये कॉनकेव है हमारा, दिस इज आवर कॉनकेव सरफेस. यहाँ से जितनी एनर्जी निकल रही है उसमें की कुछ अमाउंट जो है वो वापस इसके ऊपर स्ट्राइक हो सकती है. सो देयर इज अ पॉसिबिलिटी दैट some amount of energy will come back to its own surface that has been emitted from itself. So if this is surface 1, then what we can say, F11 is not equal to 0. However, in this case, no energy emitting from this surface will ever come back to this surface only, this surface. So what we can say that here also F11 is equals to 0. So for flat surface F11 is 0, for convex surface F11 is 0, and for concave surface F11 is not equal to 0. So what we can say here is that I just want you to remember these three terms. Now this can be surface 2. If this is named surface 2, then this will be F22 equals to 0. If it is named surface 2, then again F22 will be equal to 0. So 11 and 22 are just naming. Just remember the nature of shape. Flat shape, it won't have any incident energy that will strike on it that has left from its own surface. So for flat, that does not happen. For convex, that does not happen. However, for concave, there is a possibility. Okay, now there are some rules that are related to the shape factor. So this is our surface number 1, this is our surface number 2, and this is our surface number 3. F11 is the fraction of radiation leaving from 1 and striking to 1, plus F12 is the amount of radiation leaving 1 striking 2. F13 is the amount of radiation leaving surface 1 striking surface 3. And all of this summation, since all of those are factors and their values is less than 1, so for one surface their value will be equals to 1. This is for surface 1. Similarly, for second surface, leaving from 2 striking 1 plus leaving from 2 plus striking 2 plus incident energy leaving from 2 striking 3 is equals to 1 for surface number 2. What will be for surface 3? According to summation rule, we can write F31. F31, the amount of incident energy is emitted from 3 striking on 1 is F31, plus amount of energy emitted from 3 striking on 2 is S32 plus the amount of energy that has emitted from 3 and striking 3 is F33 equals to 1. So this we have written for each and every surface. So for every surface, the summation of all such shape factors will be equal to 1. So there are 3 bodies, so we have three shape factors for each surface. So keep this in mind. Now reciprocatory rule. What is reciprocatory rule? Let's say that we have two surfaces in contact with each other, surface 1 and surface 2. If two bodies participate in radiation, then by reciprocatory rule, what this body has area A and this surface has area A2. So according to the reciprocatory rule, A1 into F12 is equals to A2 into F21. A1 into F12 equals to A2 into F21. Fine. Now we have here known as parallel plane. These parallel planes have length equal to infinity, infinite lengths. These have infinite length. Now what happens here is, as I told you, this is a flat surface. This is surface 1. This is surface 2. For this surface, we can write F11 equals to 0. For this surface, we can write F21 equals to 0. Fine. Sorry. Not F21, F22. क्योंकि अगर 1 से कोई एनर्जी इमिट हो रही है तो वो वापस खुद से 1 पर वापस नहीं आएगी. और सिमिलरली हम 2 के लिए भी बोल सकते हैं. तो बाय summation rule, F11 plus F22 is equals to 1. Sorry, once again I'm sorry. By summation rule for first surface, F11 plus F12 equals to 1. Now F11 is 0, so F12 is 1. What does this means? कि जितनी एनर्जी 1 से निकल रही है वो सारी की सारी 2 पे जाकर इंसिडेंट यानी 2 पर जाके गिर रही है. Similarly, for second surface, F21 plus F0, sorry. F22 is 0, so F21 will be 1. F21 इक्वल टू 1 का मतलब क्या है? जितनी एनर्जी इस सेकंड सरफेस से निकल रही है वो सारी की सारी फर्स्ट सरफेस पे जाकर इंसिडेंट हो रही है या स्ट्राइक कर रही है. Similarly, we have now these two cylinders, cylinder 1, cylinder 2. Now these cylinders have same length, L1 is equals to L2. Now what happened in this case is, for cylinder 1, this is convex surface. So for 1, we can write F11 equals to 0, since 1 is convex. So by summation rule, F11 plus F12 is equals to 1. This term is 0. So what we have is F12 is equals to 1. F12 is equals to 1. Now, by reciprocating rule, A1 F12 is equals to A2 F21. What is A1? A1 is 2 pi R1 into L. A2 is, let me write it much clear way, in a clear way. A2 is 2, here, let me just write it down here. A1 is 2 pi R1 L and A2 is 2 pi R2 into L. So this is about A1 and A2. Putting this value of A1 and A2 in this equation, we get that F21 is equals to A1 upon A2 multiplied by F12. F12 is 1. So F21 is what? A1 upon A2. LL gets cancelled, 2 pi gets cancelled. We will have R1 upon R2. So just let me write it here. F21 is equals to R1 upon R2. By applying summation rule, you can further solve it. Now for these spheres, here it is 1, radius is R1. This sphere has radius R2. Fine. This has sphere 1 has area 4 pi R1 square. A2 has area 4 pi R2 square. Now this is convex. So F11 is 0, which ultimately means F11 plus F12 equals to 1. So F12 will be equal to 1. By reciprocating rule, we can say A1 F12 equals to A2 F21, which is what? F21 is equals to A2, sorry, A1 upon A2 into F12. This value has 1. Comparing from here, 4 pi, 4 pi gets cancelled. What we have remaining is F21 is equals to R1 square upon R2 square. Further, if you have to find F22, we can write F21 plus F22 is equals to 1. By reciprocating rule, put this value in this equation and you can find the value. Now there was a question asked on this shape factor. We have completed most of our important parts that we have needed to study in radiation, radiation heat transfer. So let us now check this problem. This was asked in somewhere, I think gate 17 or I don't know, gate 2005, I think. So a solid sphere has a radius R1 and a radius and sorry, a solid sphere of radius R1 is placed concentrically inside a hollow sphere of radius R2. So R1 is 20 mm and R2 is what? 30 mm. Okay. So this is 30 mm. What we have to find is the shape factor F21. F21 is we have to find. Now look at this problem carefully because this gets asked and this is not what we have studied in school also. Okay. So what we have, the surface 1 is convex. We just recently solved it. So for convex surface, F11 is equals to 0. F11 equals to 0. Now F11 plus F12 equals to 1. This is 0. So we can write F12 is equals to 1. Again, we have what? We have reciprocatory rule. What it say? A1 F12 is equals to A2 F21. F21 is what we have to find. F21 is what? A1 upon A2 multiplied by F12. This is 1. So we will not be bothering about it. F21 is equals to 4 pi R1 square upon 4 pi R2 square. 4 pi gets cancelled out. F21 is equals to R1 square upon R2 square. So F21 is what? 20 by 30 whole square, which is what? 2 by 3 whole square, which is 4 by 9. So do we have any option like this? Yes, we have. Option B is the correct answer. So this is how we can solve it. What we have used, the thing that I told you to remember for convex and flat surface, the step factor for itself is 0. Then summation rule, and after that reciprocatory or reciprocating rule. So we use just these two rules and we solve this question. So this is it for radiation. Now we have final chapter of heat exchangers. The heat exchanger are industrial devices that are industrial instruments that are used to transfer heat from cold substance to hot substance and so on. So there are two types of heat exchanger of our particular interest. One is counterflow and another one is parallel flow. Let us see counterflow. This is hot fluid. This is cold fluid. So the direction of cold fluid and hot fluid is opposite. This is THI, the temperature of hot fluid at inlet and temperature of hot fluid at outlet. Temperature of cold fluid at inlet and temperature of cold fluid at outlet. THO minus TCI will be your theta 2 and THI minus TCO will be your theta 1. What is this? THO minus TCI. What is this? THI minus TCO. 5. Now, we have parallel flow. In this heat exchanger, both of the fluids have same direction of flow. This is hot fluid. This is cold fluid. This is THI, THO, TCI, TCO. Theta 1, theta 2. Theta 1 is what? THI minus TCI and theta 2 is what? THO minus TCO. This theta, the temperature difference, is very important to find logarithmic mean temperature difference known as LMTD, whose formula is given as theta 1 minus theta 2 divided by natural log of theta 1 by theta 2. So This is a very important. This is a very important formula for us. Okay. Now there are some formulas that are required to memorize, and it is very logical to memorize here. Actually, see what will happen in heat exchanger. Here, hot fluid will lose its heat, and fluid will gain some amount of heat. So the amount of heat that is lost by hot fluid is given by QH m dot H Cph into Thi minus Tho. So we know that heat lost is what? This formula is pretty much used, mcp delta T, right? So this is what has been used in many cases. Most of these are constant pressure process, are occurring at constant pressure. So that is why we are using Cp. So for hot fluid, the heat rejected by hot fluid is what? Sorry, mass flow rate of hot fluid m dot H multiplied by heat capacity of that specific heat capacity of that fluid multiplied by the temperature difference that has happened in the fluid, that is the inlet temperature of hot fluid and the outlet temperature of hot fluid. Similarly, heat gained by the cold fluid is given by same formula, mcp delta T, mcp Tc, you can see will be greater since it will absorb some heat from this. Here also is the same case. It will absorb the heat, so its temperature will increase. So that's why it is. And the important LMTD. It is what? Q is equals to UA LMTD. U is your overall heat transfer coefficient that we will look at the end of this chapter. It is, I will explain it to you. But just remember the formula Q equals to HA delta T, and just try to equate it with this. H is what? Convective heat transfer coefficient, and U is what? U is overall heat transfer coefficient. A is surface area, here was also surface area. Here was temperature difference, here is what? Logarithmic mean temperature difference. Why there is mean is taken? Because we don't have any fixed value, it is continuously changing. The value of temperature is continuously changing at each and every instant of time. Hence, we take a mean value or an average value of temperature difference. Fine. So this was all about LMTD method. Now there are some important points that I want you guys to remember. There is a thing called counterbalance heat exchange. What is a counterbalance heat exchanger? Let me tell you. Sorry. Okay. So this is counterbalance heat exchanger. This is hot fluid. This is cold fluid. Fine. In hot fluid, here the temperature difference is theta1 and here is theta2. What happens in counterbalance heat exchanger is theta1 is equals to theta2 and these values are same. So what we test, so in this case what happens, LMTD becomes 0. So we cannot use LMTD. So instead we use AMTD or average value. We don't need even to take AMTD, we just take this value theta because it is constant at each and every instant. So we only take theta value. Okay. So if LMTD equals to 0, we need to take this value either theta1 or theta2 because both are going to be same. Now let us look at this equation. If U and Q, overall heat transfer coefficient, and Q are kept constant, we can say that LMTD is inversely proportional to surface area, and it was found that the logarithmic temperature difference for counterflow, this is what practically found, LMTD for counterflow is greater than LMTD for cross flow, which is greater than LMTD of parallel flow. Now, these values are what? These are inversely proportional, right? Right? So LMTD is inversely proportional to your area. So what we can say that area of counterflow is less than area of cross flow is less than area of parallel flow. So for same temperature difference, the smallest heat transfer that can be built is of counterflow nature. So if you have been asked a question that what kind of heat transfer that you will prefer to make it more compact in a given temperature range. So एक गिवन टेम्परेचर रेंज के लिए सबसे छोटा हीट एक्सचेंजर अगर बनेगा तो वो काउंटर फ्लो का बनेगा, इसीलिए ये दूसरा पॉइंट है. क्या है ये पॉइंट? फॉर अ फिक्स टेम्परेचर रेंज काउंटर फ्लो हीट एक्सचेंजर इज मोर कॉम्पैक्ट देन एनी अदर हीट एक्सचेंजर. ये दो पॉइंट जो है वो आपको याद रखना है. नाउ एनटीयू मेथड, स्टेट फॉर नंबर ऑफ ट्रांसफर यूनिट्स, एनटीयू का फुल फॉर्म. So NTU is equals to UA upon C minimum. Now let us see what is C minimum. UA is overall heat transfer coefficient, A is surface area of heat transfer, and C minimum. So we have for hot fluid, C hot is equals to m dot h Cph. This is known as capacity, heat capacity. For cold fluid, heat capacity is m dot c Cpc. इन दोनों में से जो भी मिनिमम वैल्यू रहेगी, द मिनिमम वैल्यू among CH and CC is taken to be C minimum. Fine. So that is what C minimum is. So this is NTU UA upon C minimum. What is the effectiveness of heat exchanger? It is the ratio of actual heat transferred to the in the heat exchanger to the maximum heat transfer. Now what is maximum heat transfer? Maximum heat transfer is the product of minimum heat capacity, the C minimum that we are going to take it from here, multiplied by maximum heat transfer. So in any heat exchanger, we know that THI is the maximum temperature and TCI is the minimum temperature. So delta T max will be equals to T max minus T minimum. तो डेल्टा टी मैक्स क्या हो जाएगा टी एच आई माइनस टी सी आई फाइन एंड फाइनली वी हैव कैपेसिटी रेशियो the capacity ratio is the ratio of C minimum by C max. So how are we going to find C minimum? Again from this method. Multiply m dot h with CPH and m dot c with CPC. Compare both value. Check which is minimum. The value which is minimum is C minimum. The value which is greater is C maximum. For condensers and boilers, CR is infinity. So the capacity ratio is infinite. Now I promised you that I will tell you about overall heat transfer coefficient. So first of all, let us have a look here in this session here. First, focus our uh, concentration on this point. There is a fluid in the inside tube. It has heat transfer coefficient Hi. The tube is made up of material which has thermal conductivity K, and outside fluid has HO as its heat transfer coefficient. So the equivalent circuit we can build. Will be like this. Sorry, one more resistance is there. Okay, let's say this is 0.1, the external is 0.2122. This resistance is 1 upon Hi into A, and this resistance is what? 1 upon pi KL ln of R1 upon R2. This resistance is what? 1 upon HO into A. So the R equivalent is this Ri plus R conduction plus Ro, right? So R equivalent can be written as 1 upon U into A. U is overall heat transfer coefficient U into A, 1 upon Hi into A plus 1 upon 2 pi KL ln of R1 by R2 plus Ro is 1 upon HO into A. So from here we can find the overall heat transfer coefficient. So that was all discussion about heat exchanger. That was a very short because of the time constraint we have. As I told you, it is not possible to complete this in so small time, but still I am giving you whatever is important from exam point of view. Okay, so this is a very important problem that was asked in I think GATE 2017. I guess I'm not sure about it. So there is a saturated steam at 100 degrees Celsius of on the outside of a tube. Cold fluid enters at 20 degrees Celsius and exists at 50 degrees Celsius. The value of LMTD. Fine. Let us draw a line diagram for it. Now, let me first of all tell me what is the Purpose of condenser. Condenser is also seen in our refrigerator and air conditioners. What is the purpose of this refrigerator? What is the purpose of this condenser? The condenser helps in changing the phase of refrigerant. If you remember this pH diagram, which is something like this, I will draw a rough sketch for you because I am not used to drawing on digital platforms, but still we can try. So yes, 1 to 2, this is for compressor. 2 to 3 is for condenser. 3 to 4 is capillary or expansion valve, and here we have our evaporator. And this is constant temperature line. Okay, this is constant temperature. So the condensation occurs at constant temperature. That is, the temperature of hot fluid remains constant because phase change occurs at constant temperature and pressure. There is no temperature that takes place because latent heat comes into action. So for hot fluid, we can draw this. THO is also equals to 100. And the cold fluid enters at, so since there is cold fluid enters at 20 degrees Celsius and it leaves at 50 degrees Celsius. So theta 1 is 100 minus 20 is equals to 80. Theta 2 is 100 minus 50 is 50. So I'll again LMTD is what? 80 minus 50 divided by ln of 80 by 50. So we need to use calculator now. Get calci. So solve this value using get calci. Ln of 8 by 5. Let me just calculate here. So the value I think should come 63.83 degrees Celsius. So check this with your calcis also. So this is how we can solve it. This is very important for condensers and boilers. Okay. So that is it for the heat transfer session. I hope that I could provide whatever could be provided in such a limited time. If you go through this lecture series, once again, then I think you will able to score at least 2 to 3 marks from the heat transfer subject, and that will be fine if it gets asked on for more marks. So I wish you all a best of luck for your GATE exams, and thank you for being here. Thank you very much.